Warning: the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This lecture is probably the first in your pre-calculus class, if you're in mine, where you're learning something absolutely new. If you're taking somebody else's pre-calculus class, usually this topic is saved to the very end, and it's all chock full of very important and yet very new material. I find that teaching this at the end of a course is a bad idea because by that time everybody's just tired, they can't think clearly, all that fun stuff. So hitting this within the first third of the course is critically important, I think. So therefore, that's why I'm approaching this topic right now. The topic itself is sequences and series. These will be all over calculus, and knowing how to deal with sequences and series is incredibly important. You will not succeed in calculus without this knowledge. Also, we will introduce in this series of videos on this topic of sequences and series a new proof style that is required for calculus. Without further ado, let's just jump right into it. In this video, we're going to be talking about specifically just what a sequence is. So bite-sized chunks here, we're just going to deal with what is a sequence. Well, by definition, a sequence is a function with domain n, the natural numbers, whose values are often written as a sub 1, a sub 2, and so on and so forth down the line. I'll highlight those, instead of using f of 1 and f of 2 and so on and so forth down the line. So we don't really use function notation that often when we're using sequences. Instead, we use this subscript notation, a sub 1, a sub 2, la da 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 da. Each of these is called a term of the sequence. So a sub 1 is called the first term and a sub 2 is called the second term. And the subscripts are often called the index of the term. The ellipses that you see at the end of this highlighted piece here just indicate that the sequence goes on forever. Now, honestly, you've known about sequences throughout your entire life. When you were a child, you might have had maybe a box of crayons and you had them ordered in a specific way from 1 to 2 to 3 to 4 and so on and so forth. Even though they're colors, they're still mapped to this is color number 1, color number 2, color number 3, color number 4, and so on and so forth. It's a sequence of crayons. You see sequences in hotel lobbies when they number rooms. And you'll see sequences in science. You pretty much see sequences everywhere. It's just that the basic beginnings of a sequence is that you're talking about a sequence of objects and they get assigned to these placeholders. Object 1 gets a sub 1, object 2 gets a sub 2, object 3 gets a sub 3, and object 4 gets a sub 4, and so on and so forth down the line. These objects need not actually be numbers. They could be things, just like I showcased with the DNA sequence. You need not have actually formulas or something like that. You could have patterns instead. So sequences are not restricted to just the mathematical world, although the mathematical world describes them the best. Essentially, whenever you have any list of objects and you just say that's my first thing, my second thing, my third thing, you're creating a sequence. That's a pretty easy to understand concept, mainly because it matches with the human mind very well. Notice sequences typically start with an index of 1. So a sub 1 is the first term in the sequence, and a sub 2 is the second term, or we also call second element in the sequence. and a sub 3 would be the third element. In real world conversations, you don't point at a box in your garage and say, oh, that's my -7th box, and there's my -6th box. We generally start with just the natural numbers. That's my first, second, third, and fourth. So anyhow, let's go ahead and try to visualize what is the distinct difference between a sequence and a function over the real numbers. Now, honestly, this says use Desmos to graph this, but you don't actually have to use any technology to see what the issue is going to be. But we'll still use Desmos to graph this because I think it's important to know how to use technology to both graph a function and the sequence that might represent parts of that function. Now, what I want to do is to showcase really how to do both functions and sequences on the same graph here. So the function f of x, we just get to use a function notation here, was given to us to be sine of 2 times pi times x. And you can see that's a very busy function. As you know from your prerequisite trigonometry material, that this is just like the sine of x, but it's wiggling really quickly. Instead of going through one full cycle in 2 pi units, it's going through 2 pi cycles in that same 2 pi units. So a little over 6 cycles in 2 pi units. Very busy function. And maybe I'll zoom in just to make this a little less busy. All right, there we have it. Now the next thing I'm going to do is I'm going to go ahead and define a sequence of points. And this is where this is going to be new to you. I want to actually start at 0 here, or maybe even 1, honestly. But I'm going to define my sequence of points as follows. So I started with just creating a list of points. This is how you can create a list of values within Desmos. I use a capital N. You don't have to use capital N, but I'm using a capital N for a very specific reason. So I'm saying create a list of numbers. I need these brackets. It starts at 1, comma, 2, comma, dot, 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 comma, and then I stopped it at 30. Every piece here is necessary. You need a beginning value. You need the next value in line to set the pattern so that Desmos knows, oh, you need the distance between each step to be 1. Got it. And then the ellipsis just says continue that pattern until you get to this value of 30. The next thing I'm going to do is go ahead and plot, or actually define the function. Or should I say the sequence? Our sequence was a sub n is equal to sine of 2 pi n. Well, I cannot type a sub n here, so I'm going to say a of n. It's just like a function, really, is equal to the sine of 2 pi n. Now, I don't actually want to see that because all that's going to do is graph over my original function up there. So let me leave that off, and you do that just by unchecking the circle there. And now I'm going to plot the points. I'm going to plot n versus a of n. Notice I'm using capitals here because n's are my natural numbered list, 1 through 30. I could have gone through 1 through 100 if I wanted to, but I just chose 1 through 30. And that's exactly how you would create your sequence. So what you're looking at here, let me zoom out. You're looking at the sequence a sub n is equal to sine of 2 pi n for the natural numbers 1, 2, 3, 4, and so on and so forth. Notice this does not look anything like the original function. And the reason why that's true is because a sequence takes snapshots. Sequences are not continuous. Functions like this, that function is continuous. I can draw it and every little dot on that curve is connected to the previous dot on the curve. And so it's just a nice continuous little curve going on forever. But sequences are discrete, which means that they plot only every once in a while, specifically at n equals 1, then n equals 2, then n equals 3. And in this case, this sequence is very special because if you let n equal 1 into the sine function here, you'll get sine of 2 pi times 1. but we know that sine of 2 pi times 1 is 0. And if you plug in 2, you get sine of 2 pi times 2 or sine of 4 pi, but we all know from our trig that sine of 4 pi is also 0. And sine of 6 pi and 7 pi, or 8 pi, and 10 pi and 12 pi, all of those, sine of those even arguments on pi, are all going to bring an output of 0. So this sequence is not only discrete, but it doesn't even display the pattern that we thought it should display. And that happens quite often. While it is true that the sequence and the base function, the function it's based upon, while they do meet up, they match at certain values, they don't match at all values. The function itself has the real behavior. The sequence just has behavior at discrete moments in time. So to answer this question, identify the differences between these graphs and state why these differences exist. Probably the very first thing I would note is that f is continuous while a sub n is just a bunch of points. They're discrete data points. It's not continuous. There's a lot of air gaps between those points. Another thing I would say is that f exhibits the behavior of the entire function while a sub n only gives small snapshots, and those snapshots are not representative of the actual flow of the function. Why do these differences exist? Well, it's mainly because with a function, you could plug in any real number into that function. The domain of the sine function is all real numbers. So the domain of the function that we were originally handed, like I just said, is the all real numbers. So sine, you can plug any number you want into that. While on the other hand, the domain of our sequence, sine of 2 pi n, all we can plug into that are the natural numbers. And so that really gets you to not see the entire pattern. You're missing quite a bit. By the way, I should mention here, to be very fair, you can have sequences that are defined not on the natural numbers, but instead on the natural numbers plus some of the integers. That's totally okay. There are sequences that start at -4 or something like that. Eventually they kind of creep their way back into the natural numbers. It's just you have a finite number of them that are negative for a little bit. Don't, as far as indices go, don't worry too much about that. That's not a big deal. It's only super useful maybe in differential equations when you need indices that are sometimes negative. But for us and our purposes, for now, we will just assume that sequences are natural numbered, have natural number domains. And finally, the last major difference between the function and our sequence, the sequence, sine of 2 pi n, where n is a natural number, is always going to be 0 because sine of 2 pi times any natural number is going to be 0, as we know from our trigonometry. So the point of this example was really to drive home the fact that sequences are functions, but functions with very limited domains, versus the function itself could be a beautiful, nice, continuous, lovely function that displays a lot of behavior and interesting things like local maximums, local minimums, intervals of increase and decrease. Sequences are just snapshots of that, and so you lose a lot of detail with a sequence. However, most of the world operates in sequences. It's not that you're getting, when you work, it's not like your boss is giving you fractions of pennies every second that you work. He or she gives you discrete amounts of money every so many hours. So that is a sequence of cash coming your way. Let's go ahead and get some practice working with sequences. Let's just find the first 4 terms of this very elementary sequence. When I say elementary sequence, I mean I've just handed you the definition of how our sequence works. And all you need to do is tell me what a sub 1 is, a sub 2, a sub 3, and a sub 4. That's all I really want to know. Nothing big here. So to do this, you say a sub 1. And basically what you've done is you've allowed n to equal 1. So that's going to be 1 to the first, or 1. And a sub 2, you'll do the same thing. you have, again, you're replacing these n's just like a function. You're replacing the argument with whatever you're plugging in here. We're plugging in 2's, so you have 2 squared. So 2 to the second power, which obviously is 4. We all know that. And a sub 3 is 3 cubed, which we know is 27. And a sub 4 is 4 to the 4th. And that is 256. You may not know that, but it is. It's very important for computer science, actually. So that's how you would start to list out the terms of a given sequence. If they're kind enough to hand you a sequence explicitly, often you're going to be building a sequence based on a pattern handed to you. So for example, somebody might hand you 1, 4, 27, and 256, and they say, this pattern goes on forever. What is the pattern? And I've said it in the past, and I'll say it to all of my students in mathematics, that really truly what you're doing in mathematics is you're discovering patterns. You're finding patterns and trying to ferret out what they mean. And so if somebody hands you the pattern 1, 4, 27, and 256, and they say that pattern continues, but they don't tell you what built that pattern, it would be your job to rebuild the sequence that builds that pattern. And we'll do that in future examples, but I'm just letting you know, more than any other material in mathematics, pattern recognition is critical in sequences and series. And that's something that honestly cannot be taught. That is something that you gain from doing mathematics correctly through all of your mathematical education up to this point. So if you have not, let's say, cheated your way through a class or something like that, if you've worked hard through courses, finding patterns at this point should be okay. But if you've kind of floundered, done very poorly, and now you're here, this is going to be tough for you. Despite that, we're still going to work a little bit on having given patterns. So in this case, again, they're giving us a pattern. The pattern is that the sequence is based upon n squared plus a -1 to the nth times n. Probably the biggest mistake I'll see with this from students is not knowing how to deal with a negative number within an exponent. That is prerequisite material, but I just want to mention this. -1 to the nth is not the same as -1 to the nth. Those two are not the same statements. The first one is sometimes, or I should say the left-hand side is sometimes positive, it's sometimes negative. The right-hand side is always negative. Those two are not the same. So be very careful. When I see that on exams, it's just, there's no way I can even give credit for you even starting the problem because you're not showcasing your arithmetic skills. So be very aware of that. Follow the order of operations, really. Use Desmos to find the first 8 terms and the 100th term of the sequence, and then graph the sequence using Desmos. Now, to be honest with you, I'd like to do this by hand first. Not obviously the 100th term, but I would like to get the first few terms just to showcase that we can do it by hand. So a sub 1 is going to be 1 squared plus a -1 to the first times 1. Well, we know that that's going to be 1 minus 1, which is 0. And a sub 2 is going to be, again, 2 squared plus a -1. This time that -1 is being squared, so it's going to become positive times 2. And that'll be 4 plus 2, or 6. A sub 3 is going to be 3 squared plus a -1 to the third, which makes it negative, times 3. So that's going to be 9 plus 3, or 12. 9 minus 3. Sorry about that. Or 6. Oh, that's kind of interesting. A sub 4. 4 squared, which I'm just going to write as 16 now. Plus a -1 to the fourth, which is a positive 4. And that'll be 20. A sub 5. I'll stop here. We get 5 squared. Let's see. -1 to the fifth, so minus. And then 5. Now, this is a very interesting sequence. 0, 6, 6, 20, 20. I wonder if that repeating pattern will continue. And so that's why specifically I say, go ahead and use Desmos to find the first 8 terms and then the 100th term, and then graph the sequence. So let's go ahead and hop over to Desmos and do that. So here we are in Desmos. I'm going to start by making my list here, my list of numbers. I'm going to start at 1 and I want to go to 100. I just need 100 in integers here, or 100 natural numbers. And then I'll define my function or my sequence. And my sequence is defined as a, normally I would say sub n, but because you're using Desmos, you have to write as a function. So a of n squared, and then plus a negative 1, to the nth, and then times n. Now notice that Desmos actually in this case knew, I think, to go ahead, oh no it didn't know to do this. It plotted points. You must ignore those because some of these points, if I zoom in, that actually breaks it. So don't worry about it. Desmos still can't plot that, but we can in a moment. We're going to go ahead and look at, we were told to evaluate this at 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10 and 100 and so on and so forth. So let's go ahead and do that. That's pretty easy to do. I will, you could either insert a table. I suppose I could do that. Let me do that here. And instead of y sub 1 over here, I'll just do a of x sub 1, just to showcase. And I'll say when x is 1, 0. When x is 2, 6, 3, 6, 4, 25, 26, 42, 7, 42, 8. And I think that's all we wanted to do, the first 8 terms. And then the 100th term. The 100th term is 10,100. So I'm going to adjust my scale here to showcase that. Now, obviously that doesn't show you anything, but there we have it. Now what I'm going to do, actually, I'll just delete all those. That doesn't really matter. I'm going to go ahead and graph all the points, n, comma, a of n. Now, let me just tell you something about this first of all. When I do that, it's saying, oh, you have a list of points, 1 through 100. Oh, you want me to plot all the x values from x equals 1 to 100, and the corresponding y values will be your sequence evaluated at those 1 through 100. So that's what it's actually plotting here. And notice it looks very nice, almost quadratic. If I zoom in though, you'll see it is discrete data and they're repeated. This height is 72, that height is 72. Scrolling over, this height is 506, this height is 506. So it is a really neat sequence where every consecutive term comes in pairs at the same height. That's kind of cool. And it looks quadratic because the actual original sequence we were handed is quadratic. If you look right here, it's n squared. Yes, it does have a minus n every once in a while, but for the most part, it's quadratic. And that's why I like Desmos so much. It's just such a nice way to visualize what you're doing in mathematics. So let's go ahead and move away from this example. We actually did everything that we were asked to do here. Just remember that you need some practice possibly on working with Desmos and building sequences and graphing them in Desmos. I highly recommend that you pay attention to this video for that. All right, let's see what we have up next. Now, here's what I mentioned earlier about needing to be able to recognize patterns. In this case, we're actually asked to find the nth term of a sequence whose first several terms are given. Now, when you read that statement, find the nth term, it really means find the pattern. Let me write that down. So find the pattern, or basically just find a sub n. What is the formula for a sub n? Remember, these we're going to assume are going to start with an index of 1. So that is a sub 1 is supposed to be a negative 1/3. A sub 2 is supposed to be a 1/9. A sub 3 is supposed to be a negative 1/27. A sub 4 is a positive 1/81. And You get the point. It goes on forever. What you want to do is figure out how did they get from A1 to A2. In this case, it looks like there was a multiplication. It looks like they multiplied by a -1/3 to get to from A1 to A2. Let's see if they did the same thing to get from A2 to A3. If that's the case, then we kind of know the pattern. And 1/9 times a -1/3 is definitely a -1/27. Might as well check the last one, right? -1/27 times a -1/3, definitely a 1/81. So, how are you going to write the pattern? That's a good question. A sub n is going to be, well, you could write it this way. Probably the best advice I can give you is to always start, I shouldn't say, well, yeah, I would say always start with whatever the first value is. I start with that, just out of habit. I have a -1/3, okay? And then I know what I'm multiplying in red by every single time. Now, I don't want to say that you're always going to have a multiplication. That is not true. I just saw it in this case that we were multiplying by the same number every single time. So I start this way and I say, okay, I'm going to put a power on something, because if you think about it, multiplication several times in a row means you have -1/3 times -1/3 times -1/3 times -1/3, or in other words, -1/3 to a power. So I'm just going to put an n here, but it requires me to check to make sure this is working, which it's not going to, but I'm just going to check to verify it. So if you try this out and you say, okay, well, what is a sub 1 here then? Oh, it's a -1/3 times a -1/3 to the first, which would be 1/9. And that is not what our a sub 1 was. So this is not going to work. I'll cross that out. Totally not going to work. But if you decrease the power on this n by 1 so that it starts a little bit later, then you'll be okay. Let's see if that works. A sub 1 is equal to a -1/3 times a -1/3 to the 1 minus 1. In other words, I'm delaying the first multiplication until I get to n equals 2. -1/3 to the 0th is 1, and so we get -1/3 times 1. That works out. Let's see what a sub 2 looks like. That's a -1/3 times, again, I'm using this formula, -1/3 to the 2 minus 1, which is to the first, and that will be -1/3 times -1/3, which is 1/9. That checks out with our a sub 2 as well. So I know that this now is the pattern. Like I said, I take my time with this because I just need to. Finding patterns is a tricky business. And so I start with what was the original value. And then in this case, we were multiplying by something all the time. So I just said, okay, well, let me multiply that by whatever we were multiplying by to a power. I tried out the nth power. That didn't work out. But I noticed that it started into my pattern a little too early. It gave me the 1/9 a little too early. So I wanted to back off that power a little bit by subtracting 1. I tried that and it worked out. Now this is not how you would write a sub n. Notice these bases are the same. This is a b to the first, this is a b to the n minus 1. You'll glue them together and add their exponents using laws of exponents from Algebra 1. And so we get the following, that in the end, a sub n is going to be a quantity of a -1/3 to the 1 plus n minus 1, or in other words, nth power. Now, a lot of people could just see that from the get-go, and that's perfectly fine. I'm just showcasing kind of an algorithmic way, I guess, you could go through this. One thing I want to note here is a terrible mistake I do often see. This is not the same as -1/3 to the nth. That is not the same. Parentheses are incredibly important here. So it is also not this. Totally different sequences. So the only true sequence is this one. That's the true answer. The rest of this stuff on the right-hand side is completely wrong. So that's our first example of finding a pattern. And again, I often just look at the first term and then I say, what's happening after that? Let's see if we could do that again. So again, we have this find the nth term of a sequence whose first several terms are given. So I'm just going to write out those terms a little bit like stacked. And looking at this, it doesn't look like you could see a pattern. It's not as if you're multiplying by the same number every time. Because if you thought that, well, to get from 1 to 3/4, you'd have to multiply by 3/4. But if you were to try to multiply by 3/4 again, it would not become 5/9. So you're out of luck with that pattern. If you think it's a subtraction, like, oh, to get from 1 to 3/4, you're losing a quarter, well, then try to lose a quarter again, and you will not be at 5/9, you'll be at 1/2. So it's definitely not a pattern like that either. So this is a cool pattern you often do see in calculus, and I find it's much better to rewrite that 1 as 1 over 1. I know, it's kind of silly, but it allows you to see a couple things. First of all, the denominators. Let's just focus in on those. Do you notice something interesting about the denominators 1, 4, 9, 16, and 25? If you're going to say they're perfect squares, you're perfectly correct. It is true. Those denominators are 1 squared, 2 squared, 3 squared, 4 squared. Notice where those numbers are coming from, the indices. 5 squared, again, the index. These indices are matching those denominators that are being squared. So now that we've figured out the pattern for the denominators, we now need to find the pattern for the numerators. Now, if you take a look at these numerators, you should notice a pattern there as well. 1, 3, 5, 7, 9. Well, those are just odd numbers. And you should recall, but if you don't, I'll help you recall right now, that even numbers are of the form 2 times k, where k is a natural number. K is in the set of natural numbers. Those are evens. Well, if you want an odd number, you either add or subtract 1 from that. So odds, you have 2k, and you could either plus or minus 1 off of that. A lot of people write it as plus 1, but that's not going to work in our situation. So I'm just going to write it like this first. So odds, you just start with an even, and either you add or subtract 1 to get to the odd number. So I could go ahead and take a look at this. This number 1, let me point at it in green, is the same thing as 2 times 1 minus 1. And this 3 is the next odd, so 2 times 2 minus 1. And this next odd number, well, is the next odd numbers. 2 times 3, again, minus 1. And the 7, it's 2 times 4 minus 1. Now, I need to draw your attention. I didn't do the last one, so I probably should just for completeness. 2 times 5 minus 1. I want to draw your attention to patterns. Here we go. The subscript, or the index on this guy, and I'm going to have to use a different highlighter here. The index here is a 1, and that happens to be this one and that one as well. The index on the next term in our sequence is a 2. That happens to be a 2. That happens to be a 2. The index on our next term in our sequence is a 3. This happens to be a 3. That happens to be a 3. Index on the next term will be a 4. That happens to be a 4. That happens to be a 4. Index on the next term is 5. 5 and a 5. So we have found the pattern. The pattern is, if you want to know what the nth term is, it's twice n minus 1 over n squared. Let me clean that up. It's 2n minus 1 over n squared. That's how you can recreate this entire sequence of numbers. So this is, again, what I've been mentioning. Like, pattern recognition is massively important in calculus and in mathematics in general. And it takes a little bit of skill, but a lot of critical thinking to kind of work your way through to figure out the patterns. It's really fun, though. It's like a puzzle. The last example, at least in this video, then we'll continue with sequences in the next video, but the last example in this introductory video to sequences is the same as the other ones. Find the nth term of a sequence whose first several terms are given. So I'm going to write down what we know are the terms. The first term is 0, the second term is 2, the third term is 0, the fourth term is 2, and that pattern just continues on forever and ever and ever. Now, I really dig this style of sequence just because it's got some flavor to it. There are several different ways you can write this, and some people can get pretty good at doing this. So let's start with just recognizing that this is basically saying I have 1 minus 1 and 1 plus 1, and then 1 minus 1 and then 1 plus 1. So that's one way you can visualize this, is that there's a center between these two numbers, between 0 and 2, and what you're doing is you're bouncing equidistant from that center every move. So the first move, you're at 1 at that center, which is 1 minus 1. The second term, you're at that center 1, but plus 1. So that's a cool way to do this. And if you do that, you can say, okay, well, this is the same as 1 plus a negative 1 to the first. And this is going to be 1 plus a negative 1 to the second. That's how I can flip from a minus to a plus 1 very easily. And this is going to be 1 plus a negative 1 to the third. And this is going to be 1 plus a negative 1 to the fourth. And if you notice, the indices here, 1, 2, 3, and 4, match the powers, 1, 2, 3, and 4. And thus, we can easily see our pattern is going to be 1 plus a negative 1 to the nth power. Now, as I mentioned, this is not the only way to actually write this. There's some very cool ways you could do this as well. So one of the cooler ways to do this, I think, is to use a trig function. And even with the trig function, there are two ways to do it. But you could say, oh, a sub n is equal to, well, again, you're centering at 1. But what you want to do is add or subtract 1, right? Well, we know that, for example, the cosine hops between 1 and negative 1 at multiples of pi. So I could say, let's say, plus the cosine of n pi. Of course, then I have to check this. So, because it might not work. So let's go ahead and try it out. When n is equal to 1, you get 1 plus the cosine of 1 pi. And the cosine of pi is a negative 1. And so that's 0. And that does work out. If we try 2, 1 plus cosine of 2 pi. Well, cosine of 2 pi is 1. So that's going to be 1 plus 1, or 2. Okay, so the pattern will work out, actually. You could keep trying. That pattern will totally work out. So that's another way to write out that sequence. And this is what's odd, or I shouldn't say odd. This is what's a little bit challenging when you're using online homework systems, because I used one in the past by a publisher, and I had students entering in this style of answer, which is absolutely correct, but it wasn't taking that answer because it was coded to only take one style of answer, this one right here. And that's a shame, because I love to reward creativity, and there are very creative ways to do this problem. All right, so that does it with the pattern recognition here. In the next video, we'll go ahead and start talking about different types of sequences, specifically recursively defined sequences.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.